that we would implement debris mitigation processes on every launch. And it required a massive redesign of every spacecraft. Every screw holding a spacecraft now is retained with a wire to the body of the spacecraft. So if it works loose, it can't float off in space. That level of detail has been implemented right through the space industry. And it was implemented in every major space country. So not just the ones we like to think of as responsible countries, but frankly, every user of space implemented this. And you can see the impact was that in this 9-year period, the growth rate of space debris was a third of what it had been before. And we thought we had bought ourselves 50 years to solve the problem. Then a couple of unpleasant things happened. But the point I'm making here is there was no international law. As an international community, we were actually smart enough to come together, make voluntary protocols, because it would have taken 15 years to get laws passed. In fact, we've tried in other domains that I've been involved in, it's taken 30 years and we're still not there. So it was decided there would be voluntary protocols, and they worked. But what happened next was two events. One, very deliberate, which was a Chinese anti-satellite test. For whatever reason, we will never know. It was designed to create a massive injection of debris in the most popular orbital plane in use even to today. So we have, you see here, a very significant growth in debris. This is due entirely to a single deliberate event by the Chinese Ministry of Defence to deliberately fire, and it's a technological tour de force, no mistake. If you can actually fire a missile and kill a satellite at 800 kilometres, that's a pretty strong demonstration of technical capability. Very few countries on Earth could do it, but very few countries would want to, because this is what happened. So we lost 30 years. We lost 30 years. And then what happened was what we'd been fearing for a very long time, which was we had the collision I showed you a few moments ago, where two satellites collided and generated another step function. Can't make this work properly, but there we go. Another step function in debris here. So it moved us, in the space of 2 years, we went from having the luxury of at least 30 years to prepare for the doomsday event to having something like 10 to 15 years. The optimists in the statistical community think it could be out to 20 years. Some people believe we're at about 10 years. And I want to give you, so I'm just here highlighting that these two events generated a significant amount of debris, but behind the scenes, there's another effect going on. There is now enough debris that debris-on-debris collisions is generating even more debris. And we're really struggling to monitor that. And here I'm only showing the largest debris. And here I'm just showing, this is the Fengyuan ASAT, anti-satellite test the Chinese conducted. So the red line is the debris after the test, and the blue line was the debris before the test. And if you look at the population distribution of debris, you'll see this is a very popular debris band. Why? Because this is one of the most useful satellite orbits for low Earth orbit satellites. 790 kilometres to about 830 kilometres is a very sweet spot for a lot of human resource management, communication satellites and so on. And so good luck or bad management, bad luck or good management, who knows, we have got a massive increase in debris in one of our most crucial debris zones. This shows you what the population distribution is, and this peak here is exactly where the Fengyuan debris injected, and it also happens to be where the Iridium Cosmos collision happened. So you see very high peaks of debris. So it would be even okay if we had as much debris as we have, but it was distributed evenly through space. It's not. It's very dense in the areas where we like to go because they're the best orbits for us to work in. So why do we care? As a society, why do you think we would care? Well, the answer to that is Australia is the most dependent country in the world on space. And very few people, Australians, know that. We don't have a space launch facility. Some people like to spread rumours we don't have a space industry, but we are the most dependent country in the world on space. Why? Because we are a very advanced economy, occupying a large continent with very few people. The only way we can manage our affairs or manage our industry or manage our crops efficiently is using space resources. And I'll step through that. We're really heavily dependent on space for all these things in Australia. Navigation, comms, time. Why is time important? Time is fundamentally important to all communications. Your cell phone doesn't work without space. And people look at me sometimes and say, wait a minute, my cell phone works off the cell phone tower. But the synchronisation of all cell phone communications across Australia so that the packets of data won't interfere with each other is all done by satellite. Resource management, all the crop management optimisation, the water management, all done from satellites. Law enforcement, border protection, weather monitoring, climate change. The very few people in Australia know that the facilities operated in West Australia and here in Mount Stromlo by Geoscience Australia are two of the most fundamental climate monitoring sites in the world for measuring sea level change. Without those two sites, we would not have the absolute evidence of how fast sea levels are rising or not rising. Those two sites have contributed in weighted average at least 40% of the solutions for the global measurement of sea level change over the last 10 years. Worth thinking about. Emergency fire and rescue, defence, many of you will know this. So the Commonwealth has a policy. As a country, our space policy has one line. This is it. Achieve ongoing cost-effective access to space capabilities on which we rely. So the nation's space policy is not about building bigger spaceships. It's not about having the best laser communication systems. The nation's space policy is preserve the environment because we rely on it. Our economy needs it. And the economic and social impact of losing space through a catastrophe of debris avalanche would be quite devastating. No one in this room has lived through a recession the like of which we would have if we lost space. We would probably lose 5% productivity across the top of most of our industries. The cost of your groceries in Woolies would go up by at least 5 or 10%. Why? Because the just-in-time delivery systems rely on satellite traffic management, warehouse management, and just-in-time delivery of goods which can only be facilitated and managed using space technology. Who would have known? Woolies in space. So this is just a graphic to remind you how utterly dependent we are. You cannot even pump fuel at a gas station, fuel station, without space. It doesn't work because the ATM, the electronic reading on your credit card, the anti-fraud provisions rely on timing processes that are synchronised through satellites, not by landline. Just again, a graphic example. This is a satellite picture of a bushfire in Australia in 2013. Shows you very graphically, one picture. You see the town, Lithgow, you see the fire, you see which way the wind is blowing. You can look at this and say, well, the town is safe for the next hour or two because another satellite will give you the wind pattern. Another satellite will tell you where the cloud is. So the whole emergency management of things like bushfires, which are really important to us in this country, is migrating towards satellite channels. And this kind of capability right across the board can be lost overnight, literally in the space of a day. So I just wanted to go over what the trends were up until the last 4 or 5 years. So there are only about 3,000 operational satellites, but they are worth about $1 trillion. $1 trillion. And the $1 trillion, that's just the satellite value. Nobody I know, and I'm in the space business, nobody I know will launch a satellite unless they have $3 of economic activity for every dollar of asset they have to put in space. So there's trillions of dollars. A good example is you buy a taxi to run a taxi business. The taxi is not the business. The taxi is just the asset that operates the business. So we've got a tremendous dependence on space. And the $1 trillion speaks for itself. But there's also 300,000, so the useful objects are kind of outnumbered. If this was a war of numbers, they would be losing very quickly. The massive number of debris objects in space now. It's mind-boggling to think how we achieved this. And if this has been set as a stretch goal for us in the 1950s, we would have said, gee, not sure we could get that much debris up there that quickly. But we did it. So the risk is increasing. That's obvious. You've got more satellites up, more value going up in dollar value, and you've got more debris being generated. And even now, when every country, including China, is adhering to the protocols, debris is growing because the numbers have been lifted to the point now where the debris is reproducing itself. So this is the controversial line. None of us like people who say the sky is falling, sea levels rising, which they might one day. Nobody wants those kind of Cassandras, but the fact is that we predicted this in the mid-90s. We predicted that about now we would be losing 4 or 5 satellites a year. Guess what? We're losing 4 or 5 satellites a year. It's only, in dollar value, it's about 200 million, which is nothing. We could lose 2 billion. It's still a very small percentage of the trillion. That's not what's important. What's important is to know where the line gets crossed when this becomes irreversible and the process accelerates a lot like a nuclear reaction. It goes to the point where it becomes a runaway process which we can't control. Not that we're doing such a good job of controlling it now. And the best scientists and the best models, verified by now 20 years of observations, measuring debris, measuring the collisions, the models, the earliest date they show for the 50% probability that we're going to lose space is in the 5 to 10 year range. Most of the models fall between 10 and 20. So the fact is that I'll pick a number, I haven't calculated it properly, but there's a 5% chance we could lose space this year. So if there were 20 universes and 20 Earths, one of those Australias would lose access to space this year. So it's not a very comfortable place to be. And this is the one that rocked everyone. When we started looking at this in the mid-90s, and yes, I was involved in this in the mid-90s, the global community had invested $20 billion in tracking assets to try and track the debris, and still had only got to 10%. 10% with 20 billion. And so basically every government walked away from solving the problem. Everyone got on board to try and slow the problem down, to mitigate the risk, but there was not one government in the world that would say, we'll take a step forward, we will do something. So really, a completely new approach was required because the forecasts were $100 billion to solve the problem, and look back through what happened in the mid-90s and onwards. There was, as there is today, crisis after crisis. Governments don't have the time or the energy to focus resources on this. So now I switch to Australia and why we have the coolest science project in the world here. So very few people know that Australia has been a world leader in space tracking, that is, using lasers to track things in space, not radars, but lasers, for 40 years. 40 years we've been the #1 country in the world. And in '96, about 20 years ago, my research group proposed a new solution that could solve the last 90% of the problem for less money than we'd spent on the first 10%, which seemed to me like a good deal. And eventually we got a few people to listen. So what happened was we built the prototype in '97, tested it, it worked. This is tracking. This is not, I'm talking tonight about moving debris in space with lasers, but the first step towards moving it is knowing where it is. You can't move something if you don't know where it is first. So the Australian solution for tracking was proven to work in what we call a technology demonstrator, which is not even a prototype. We cobbled together telescopes and lasers and all kinds of stuff and fencing wire in the Australian tradition, and we made it work. So what happened since then? So 20 years. We've been in 20 years of refinement. And we now are deploying significant numbers of what we call sensors. These are laser trackers. And these laser trackers will be sufficient to track all the debris that we're concerned about. And I don't really want to go into it here because it's not a subject for tonight, but all of that infrastructure is being deployed by one company at its own cost, which is EOS. That's one of my day jobs. So by 2018, excluding the US, Australia will be the largest contributor of space debris data in the world. So if you know where it is, the practical solution, once you have the debris data, the information is, every satellite can manoeuvre, and if they're given accurate enough information about the collisions that are about to happen, they can manoeuvre around the debris, go back to their original course, and everything's fine. The problem with that is, and we get down to how the global economy really works. The problem with that is most of the satellites are owned by private companies. And the private companies, many of them, they're not governments. They don't always operate socially. They will often rather take the risk of collision than manoeuvre the satellite. Why? Because a satellite lifetime, and therefore its useful period commercially, is governed by its fuel load. When it runs out of fuel, it's commercially useless, because a satellite, again, most people, you don't need to know this, but I'm going to tell you, satellites have to manoeuvre all the time to maintain an exact position to fulfill their function. It's minute amounts of fuel, it's grams at a time, but you have to burn fuel to just stay exactly where your users on the ground expect you to be. And when that fuel is completely consumed, the satellite is useless. It will drift away from its expected position and it can't be used anymore. So burning fuel on a major diversion to go around debris is very difficult to justify, particularly if the information is poor. So the track record in the past is nobody ever manoeuvred a satellite to avoid debris, because the tracking information on debris for the whole world had an error, an uncertainty on the collision of 5 kilometres. So if you've got to move your satellite 5 kilometres, firstly you're going to have to move a lot, because lots of things, and I'll show you how this works, but lots of things fly into that 5 kilometre circle. So what Australia has done is we've proposed to put 100-metre bubbles around these objects, around the satellites, and we will only give an alert when something is going to fly into that bubble, which means the average satellite in 10 years will get one alert. Instead of one a month, they'll get one every 10 years. And when they get the alert, they're going to move, because they only have to move 200 metres, not 5 kilometres. But all that said, moving the debris would be much cooler than moving the satellite, because then the satellites wouldn't have to move at all. And moving debris becomes important because a lot of the collisions we want to avoid are debris on debris. Remember, there's two things. We want to preserve the satellite assets because that's our commercial life, but we also want to stop debris from hitting debris because that's the debris reproduction process. We want to do both. The nice thing about the Australian technology, which is unique in the whole world, the rest of the world uses radar. Radar can't scale up. The nice thing about laser tracking technology is there's a thing on the side of the laser called the volume button. You turn that up and the power goes up and up and up, and you can, I'm joking. Yep, they're completely different lasers, but it's scalable is what I'm saying. It's scalable, and you can scale the laser power to achieve lots of different outcomes in space. And I've got here a couple of cartoons. The top one is a space facility we built in Europe, and the lower one is a picture of the facility that we're using here in the ACT for most of the experiments. To give you an idea of how well placed Australia is, one company has deployed over 500 million of laser space tracking assets globally. And no other company in the world is within 15% of that. In other words, one Australian company dominates the whole world in laser space tracking. So that brings us to the Space Environment Research Centre. And how did this come about? This came about because Australia, as I've said, was the #1 country in the world for space tracking. Space tracking with lasers is the only scalable technology. So we already had a feasible platform, scalable technology where we can increase the power and actually move things around in space. So the Commonwealth Government and EOS and 5 other participants formed what's called the Cooperative Research Centre. And the budget will sound very modest when I tell you what we're trying to achieve, but the total operating budget for this organisation is only $60 million. And of that, only $20 million came from the taxpayer. The other 40 came from the participants. But what's not expressed there is there's a couple of $100 million worth of relatively new space tracking and large laser infrastructure that has been loaned into this organisation to accelerate the research. So we have a $60 million budget over 5 years, 3 of which have expired as I stand here. We have 2 years left. And I'll come back to that shortly. So what's our goal? Our goal was simply to demonstrate that debris can be moved with lasers and that the technology is technologically achievable from Earth, technologically achievable and scalable. So how do we actually manifest a solution to the debris problem? There are really 2 steps. The first one is slow the growth of the debris. We want to get that curve flattening out again because we need to buy time. We need probably 10 years to deploy a real solution to the debris problem. And we don't know if we've got 10 years. So the most important thing we need to do first is slow down the growth of the debris. So how do we do that? The first thing is improve the accuracy of the debris, of knowledge of the debris. Track more of it and track it 50 times as accurately as it currently is tracked. That's another nice thing about the Australian laser technology is it is 50 times more accurate than anything that's ever been done before. So tracking with lasers is probably the right solution. The other thing we can do is get more strict compliance with the protocols, and I can tell you that is happening. I don't know of any reckless, I'm talking in the lower orbits, very few reckless operators left in space. Moving debris to avoid collisions using lasers. This is going to become important for certain classes of debris. I hope I don't forget to emphasise later. This whole project is aimed at solving a slice of the problem. That piece of the problem is a certain type of debris that lends itself to our laser interactions. I'll talk more about that later, but there is an international solution that's being mounted to the whole debris problem, and we're a very important part of it, a unique part of it. The second part of addressing this issue is to actually reduce the debris population, because while it's up there, think about it, if there's a 5% chance we can get a debris avalanche this year and nothing gets added, that means in 20 years we'll lose space anyway, give or take. So reducing the population is really important. And when you think about it, you want to reduce the population by taking out the biggest objects first, because when they collide, they generate the most new debris and therefore increase the probability of losing space even faster. So removing the largest debris using capture satellites. This is not an Australian program. You need to have a launch site, you need to have very good satellite technology. So other agencies in the world are working on the large debris problem. Removing debris using lasers, it turns out, and you don't have to be real smart to work this out, but the lasers don't exert huge forces in space. The lasers exert what I would call modest forces in space, because we can't use really big lasers because we'll damage the debris, and we don't want to do that. We have what we call the Goldilocks syndrome. It has to be not too big, not too small, it has to be just right. Because if the laser's too small, you won't move anything. If it's too big, you'll break the debris in half and make the problem worse. So it's a process of having exactly the right manifestation of the force models and the surface interactions with the energy that you're projecting to create the phenomena that you want. I'm highlighting in red here where Australia is making a major contribution. So of the 5 key domains for space debris mitigation, Australia is making a significant contribution in 4 of them. And those of you who are paying attention will notice that I said we didn't have a significant role in removing debris because we're not a satellite launch country. But it turns out that our technology is the best technology for characterising the debris that's up there. And so when you want to select, when you need to know what is the large debris and how fast is it tumbling, it turns out tumbling is really important, because if it's tumbling too fast, you can't grapple with it with an intercept satellite to bring it down. So one of the key things that our technology does is we detect, and I'll talk a little bit about that soon, we actually measure the rotation rate of the debris so that the grapple missions can actually plan their missions properly. Very quickly, this was the SERC plan. We had the four boxes, the 4 research programs in SERC, and the one that we all kind of focus on is this box at the bottom right, which is the manoeuvre box. Manoeuvre is a fancy word for pushing debris with lasers. One of the key things I should have highlighted about SERC is it is an international program. So we have US, Australian and Japanese participants in SERC. It's a small organisation because when we planned it, we needed to run very hard, very fast, very lean and very aggressively. And you don't do that with an organisation which in itself comprises more than 20 other organisations. I want to give you some statistics on collisions now. So if we just take the largest 20,000 debris objects, and if we have a 5-kilometre circle of uncertainty around a satellite, we have 42,000 potential collisions a week. And that's the current state of the art of world debris knowledge today. If we have 1 kilometre drops to 3,000 a week, 500 metres, 700 a week, and at 100 metres it's down around 100 collisions a week for the entire population of satellites. So just improving the knowledge means that you get certainty about when the collision will happen, and the number of collisions drops such that the amount of fuel you would use to avoid those collisions is minute compared to if you had to do 42,000 manoeuvres every week. So, as I said, 5 kilometres is typical today. And interestingly, I put up a slide earlier about the collision between 2 satellites. That was predicted with a 500-metre uncertainty. So someone went to the trouble of retracking the satellites and saying, oh my God, it's not 5-kilometre miss, it's going to be within 500 metres. Even then, 500 metres is 700 a week collisions alerts. The user of that satellite, the operator of that satellite said, at 500 metres, I'll wing it. And we saw from before what the result of that was. So our objective in Australia, and we're delivering on this, is to give 100-metre errors. So we will solve for the commercial operators the conflict about whether they want to operate safely and properly or economically. We can take that problem away. So at that point, manoeuvre can protect all the satellites. And so you're then left with, well, what's left? What's left is the problem. We then have to stop the debris from propagating against itself and multiplying. So debris manoeuvre and debris removal are still key priorities for all spacefaring and space operating countries, which is basically most of the people on Earth. I'll come back to this. I know you've seen this. This is just to remind you what happens when we get it wrong. This is burned into the mind of all the space operators in the world today, because this could have been avoided. And by the numbers, this collision alone, on top of the Chinese anti-satellite test, this collision probably ate up 20% of our error margin before we lose space. And we don't want any more of these. So how do we move? I get to the interesting part now. This is the science. It's really a high school science project run by grown-up high school students. How do we move objects in space with lasers? It's really simple. It's photon pressure. I am managing to stand here in front of you despite the fact there are lights above me pushing down on me. I'm just barely managing. There is probably nanonewtons of force falling on my body from those lights. And the trick is simply, and it's been known for a long time, if you have sufficient irradiance, in other words, sufficient intensity of the beam, you generate what can be quite significant forces. I mean, if I had a 200 watt laser here and a 2 centimetre piece of aluminium foil, I could propagate it across the room, provided it was in a vacuum and didn't want to fall down. So this is how it works. We have an object flying in space, we put a laser on it, it produces a net force in this direction. Over a period of time, the principal effect of that force is to slow the object down a little, a fraction. And the typical engagement efficiency of, we slow this is moving at 10 kilometres a second, and we slow it down by 0.1 of a millimetre per second. But that is enough to move it 200 metres within a day. So we can change its position where it was going to be versus where it now will be by 200 metres just by moving it 0.1 of a millimetre per second. And so what happens is we modify the orbit this way. And what do you need to do this? The key elements are you need a really big telescope, because to deliver a beam at a long distance, the longer you want to effectively, we call it focus, it's not the right term, but the further away you want to focus, the larger a telescope you have to start with. You need a really big laser. You need beautiful pointing accuracy in the system. So most people here are used to degrees or radians or milliradians. EOS, the company that belongs to the CRC, has been building for the last 20 years 30-tonne, what we call beam directors. They're laser directors that can point a beam to a point in space with an accuracy of 0.1 of a microradian. So that's one of the Australian technologies. You need to have like 50 of these things before you can make something like this work. And Australia had 40 of them, and no other country in the world had 20. So this was the only place we could do this experiment. This was the only place we could mount this campaign to start building this infrastructure. And the last thing you need is atmospheric correction. Now, in this technology, there's probably 50 hours of really cool technical talks. I could talk to you for hours about the laser. I could talk to you about the telescopes and the pointing and all those cool things. But I thought one of the most interesting things for me anyway is the atmospheric correction, how we deliver the energy into space, because that's actually the hardest part of this whole experiment. So this is how it's supposed to work. So we have an object here. Sorry, it's actually here. We think it's here because this is where we see it. Remember, we see it after light travels at a certain speed, and for typical objects it takes 4 or 5 milliseconds for the light to get to us. So we're seeing where it was 4 or 5 milliseconds ago, 10 kilometres a second, it's moved quite a way. So it's actually here, we see it there, and if we want to hit it, we need to fire the laser here, because we need to point the laser where it's going to be. Not where it was, not where we're seeing it, which is where it was, and not where it is, but where it's going to be. So you would think that's pretty simple. And in fact, in the tracking context, this is what we have been doing in Australia for 40 years. This is called the point ahead angle. We point the laser ahead, we track with exquisite accuracy. These systems have been refined, for example, for sea level monitoring. We track objects with 0.5 millimetre accuracy at 10,000 kilometres, so we can measure the sea surface globally to 1 millimetre in height. So this technology is just exquisitely refined in this country. The problem is, this is what really happens. And for tracking it doesn't matter, but what happens is the beam doesn't propagate nicely. And thanks to ANU for the slides. And the beam doesn't propagate as well as you would like to. Because of the atmosphere is made up of imperfect layers, which are controlled by both kinetic energy, which is the movement of air, plus there's a thermal energy which creates turbulent cells. So you can, a football's about the right size. You have to imagine, a soccer ball that is, you have to imagine lots of soccer balls of air which are acting independently of other soccer balls, and that's how the atmosphere is made up. And to put a beam through that means the beam gets very badly distorted. and it gets distorted and it loses its shape, and you don't control the delivery of energy from the ground into space. Now, astronomers have known about this for a long time, and the inverse problem has been solved for the last 25 years in astronomy by looking at a star and monitoring the light from the star and basically putting it into a special sensor that senses the fragmentation of the atmosphere, the turbulence, and corrects for it by distorting the mirror that you're looking with. So the mirror is the inverse of the distortion of the atmosphere. And what comes off the mirror ultimately to your camera is a perfect image. And so one of the leading institutions in the world for this technology is ANU, and ANU is a member of our organisation. This is the Space Environment Research Centre. And so what we postulated is, let's turn this upside down and use the same technology to pre-deform a mirror so that the laser beam is launched into space imperfectly, but the imperfection is the exact inverse of the imperfection in the atmosphere. So we will get a perfect propagation of the beam through the atmosphere. The problem with that is we don't have a star and we can't use the object because the object is back here. The light from the object is of no use to us in terms of finding out what the atmosphere is doing over here. So what we actually do is we have another laser. The system gets more and more complicated all the time, but there's another laser. It's called the guide star laser. And the guide star laser is an orangey yellow. It's the most gorgeous colour. Other than 532 nanometres, I think it's the nicest colour in the world. It's a beautiful orange colour, orangey yellow. And what this does is it excites sodium atoms that are at about 90 kilometres in altitude, and the Earth's covered in a blanket of sodium atoms, which just happen to re-radiate like an artificial star. And so we use one laser, which is pointing ahead of the object, to stimulate an artificial star. Observing that star's imperfections with a monitoring system allow us to deform the mirror that we then use to fire the laser in advance of the debris object, so that when it gets to the debris object, it's perfectly shaped. Without this, the beam would be very splotchy and about 10 metres wide. With this thing operating, it's about half a metre. So we deliver tens of kilowatts of energy into a spot about this size. And that does some serious pushing. So where are we now? This system we were funded 3 years ago, and at the during funding process, basically we said, well, 5 years, the normal funding is for 7 years. We said, well, 7 years isn't enough, but we'll know in 5 years whether it's going to work, and we'll terminate if it's not, and we'll extend if we need more time. It now kind of looks like we're going to be ready inside 5 years. So this stuff is coming together so fast now, we will be bolting it together. All of it will be ready as subsystems by 15 months from now. So it's been in intense development. And it will be operational around about Christmas of 18, 6 months before the 5 years is up. So it does seem like we are well ahead of schedule. And look, this all works at various levels. Most pieces of this system have now already been tested, but the integration of this is, as a major project, this takes about normally 2 years, and we're about 6 months into that process now. And it is going very well, very well. And bear in mind, we have done this many times over 40 years. That's why this project is being done here. So we think there's a very good chance of success on this particular aspect of our project. So this is just a picture of where we're doing all this. This is the EOS Space Research Centre at Mount Stromlo. So EOS is one of the companies that's a member of SERC. It has a very expensive and exquisite research centre at Stromlo. This is the telescope dome that we use. It's a 2 metre class telescope. Don't know what happened there. And this 1 metre dome is actually owned by Geoscience Australia, and it's a sub-millimetre accuracy laser tracking system, also designed, developed by EOS. And that system is used for scientific measurements in space at the millimetre level, including probably the most topical of those is this is one of the most fundamental measurement sites in the world for sea level change. who'd have thought, everyone thinks you do sea level change down by the waterside. But in fact, there's $400 million worth of $600 million now of satellites flying around with nadir pointing laser altimeters profiling every piece of ice and water, lake, fresh water, every piece of water in whatever form on the planet continuously. And the volume measurements of that ice, water, are computed fairly regularly by all the major agencies. But the measurements are only as good as the orbit determination of where that satellite was flying. And so this is the fundamental southern hemisphere. There are two fundamental southern hemisphere sites, both controlled by Geoscience Australia for monitoring that. Nothing to do with space debris, except space debris could wipe out our altimetry satellites as well. That wouldn't be good. So another aspect of our work that impacts the large debris capture program is the tumbling program. And this is really pretty interesting work. So these programs basically involve taking a satellite, we create a model for the satellite. We then, what you see here is two graphs. I don't know whether you can see it properly, but you don't need to read it, it's just red and blue. One is the simulation, which is what we think that object will do in space, and the other one is what we actually measure. Because with our telescopes, we can actually do photometric measurements, and we can measure, using glint angles off debris, how fast the debris is tumbling and which axis it's rotating on. And it's very important if you want to engage with that in a proximity mission to grapple with that satellite and attach to it something which will make it deorbit. So what you get from that is observations like this, which very specifically tell you this satellite would not be your prime target, or this satellite should be one of the first ones you go and try and deorbit. In this case, this is a dead satellite. A good example here is there are 36 dead GLONASS satellites. Now, GLONASS is the Russian equivalent of GPS. 36 of those have died on orbit. And the orbital planes are shown relative to the blue, which is an Optic geostationary satellite orbit. So they're really quite high. And these measurements, these black dots, are the measurements taken of the tumbling rate of those GLONASS satellites. So if you wanted to go and deorbit those, you would prefer to be taking these ones out first because they're tumbling much more slowly. A satellite that's tumbling with a rotation rate of half a hertz is virtually impossible to grapple with. It will destroy you rather than you destroying it. And of course, later we will get the technology to grapple with those as well, but we don't have that today. So I want to give you a quick update where we are in this program, because we're basically midterm. We're 3 years into a 5-year research program, and this doesn't end at 5 years. When we get to 5 years, the research and the activity has so much momentum that it's just not possible for it to stop. So there are significant extension programs that will couple to that one way or another. So what we've achieved so far is we have achieved major improvements to debris orbit uncertainties. So we can, as of the second half of this year, we will be publishing 100-metre type miss distances for the collisions that we're interested in. That will already be a very big contribution, just in orbit determination. We've made significant improvements in the debris attitude management. So this is what I was talking about, the tumbling measurement. So we will be able to provide data to NASA, JAXA and ESA, who are all designing grappling missions for the really large pieces of debris. And this database will be expanded to deal with all of their initial target sets. One of the things that, because we're a CRC, we have we're all about public good, but we also have a public education element to the CRC, and we have stimulated a very significant increase in education in doctoral and postdoctoral work in space in this country. I hope within another 2 years, irreversibly, I hope we'll have at least 20 or 30 space PhD graduates by the time we get to the end of the CRC, and that's just about enough to kick off a significant level of expertise, particularly if it's focused on areas where we really add value. One of the things that has changed is the activities that I've spoken about that we've done for 40 years were essentially in a military domain, so they were not public. So this activity has surfaced a whole range Australian expertise and technologies that were otherwise never heard of internationally or even domestically. So Australia's standing internationally in space has increased, I think, quite dramatically. We've also made already a significant contribution to preserving the space environment and the economy, and we hope there's still enough time before we hit the 50-50 point on Kessler. And at that point, I want to stop and take questions. Thank you.
I was told to come up at this point, but I don't really know why. But I will say that there are 2 microphones wandering around the lower floor, and if you'd like to ask a question on the upper floor, there's a microphone right just zap bang in the middle. Thank you.
Thank you very much. Does the miniaturization of spacecraft contribute to reducing the odds, or does it just mean that there's likely to be more objects that are launched?
The miniaturisation of spacecraft in almost 98% of miniature launches is into the 300 to 500 kilometre altitude band. And I didn't mention in my talk, but the higher you launch, the longer debris stays there. But there are 2 elements here. One is the smaller satellites go into very low altitudes, which decay within 10 or 15 years. The higher, the more popular orbits, they decay in 500-600 years. And once you get above 1,000, it can take thousands of years. And at GEO, it's never. It will never decay. Once you put junk into GEO, and GEO is the most valuable real estate on the planet. There's only one very narrow band of orbits around the Earth, which will take geostationary satellites. And once it's contaminated, it can never be replaced. So the proliferation, I think, is not a serious problem for us. Partly also because almost all the launch agencies that are putting those thousands of new satellites up, most of those launch agencies are mandating the code of conduct, which means everything that's put up has to have the power to bring itself back down again and not contribute to the problem.
Thank you very much for that talk. That was brilliant. Could I just ask, though, you were saying that when a satellite runs out of fuel, it's not able to maintain its position on station. Given that you've got such accurate tracking technology, wouldn't you be able to extend the life of that satellite by being able to feed back to the operators of the satellite where it is?
There are some economies that come from that, but the real issue is when you're out of fuel and you lose station. Where this technology can help, and it's really the next level up from what we're experimenting with here, it's much more powerful lasers, is we can, right now a satellite operator has to turn his satellite off when his fuel, not when his fuel runs out. The code says you turn the satellite off when the fuel burns down to the amount of fuel you need to drive the satellite to burn up in the atmosphere, the deorbit fuel. And there is some potential for this technology to allow satellites to run until the tank is empty, which means a 20% life extension. So that means a 20% reduction in your phone bill or everything else, because the laser will take that satellite and bring it down for you. But we're more than 10 years away from that.
Okay. You talk about the disaster scenario and what Australia could lose, and one of the major things we could lose is communications. It occurs to me that with all this debris floating around and increasing, a useful percentage of it might be reflective to radio waves. Do you have any concept of exploiting that for communications purposes?
Not directly for communications. We've done a lot of experiments in the last 25 years, believe it or not, using free-to-air television as our transmitter. And these debris objects, up to about 1,000 kilometres, do retransmit the broadcast back to us. And so we can actually track some of it using TV broadcasts. Problem is free-to-air TV is dying worldwide. And not only that, the tracking is very coarse. It's kilometres in uncertainty, whereas the laser is very, very accurate.
Thank you, very interesting talk. You've partially answered the question I was going to ask, and that was, are you able to actually bring the debris into burn-up tracks so that they actually burn up in the atmosphere?
Well, you use the present tense of the verb are, so the answer is no, but that is the ultimate goal, is to use this technology to deorbit about 20% of the debris. So the technology only lends itself to what we call high area to mass ratio debris. So you need to be big but light relative to your size, and there's lots of debris that's big and light. The side panels off rockets, aluminium foil floating around in space. There's lots of things that are quite lethal and dangerous to satellites, but they're light relative to their size. And so a good 20% of the debris can be taken out of orbit permanently by this technology from Australia. And it takes about 10 engagements. So it has to fly over 10 times. But Australia's a big country, and all the debris flies over us very often.
Dr. Greene, I was just wondering, with the prototype in 18 months going live, what's the mass range for targets that you will be looking at practically affecting their orbits?
Well, for the experiment, we're cheating. For the experiment, we've put our debris tracking and classification assets online, and we're down selecting what we think are the 100 most useful candidates for testing the technology. And we think of the first, we've already down selected to 200, we'll down select to 100 objects, because we've got tremendous capability to research the individual debris. Believe it or not, every piece of debris has got a catalogue number. And so we're down selecting, but in the longer term, I would think we'll be looking to do objects that are bigger. So the question you asked was how heavy? Probably up to a few 100 grams initially, and then we'll go up into the kilogram class. Bear in mind that the average dead satellite is about 150 kilos. So there's a way to go.
In your talk, you said that Australia is a significant player, the most significant player. How did that happen?
I think it was an accident. No, it was an accident as much as you got to go back 40 years. Why did we become so prominent in this field? Because we're a big country, and to do sensible space observations, you need a good baseline. And no other country in the world wanted to do optical observations because it could be cloudy. But in Australia, it didn't matter, because if Perth was cloudy, Brisbane wasn't. If they were both cloudy, Alice Springs wasn't. So we had enough space where you need 4 different weather systems to simultaneously be bad to take us off the air. So the principle that we used was what we call geographic diversity. So because we had that and good weather, and we had a very good astronomy community back in the 60s. And so the astronomy technologies leaned into what became optical space tracking, which leaned into laser tracking of spacecraft. So it kind of was an accident of nature and history. But we've excelled for the last 40 years. And there's been a lot of very bright people throw themselves at this. I didn't do them justice to say it was an accident.
Thank you so much for that talk. I was just wondering the legalities around Australia using lasers to move debris that still belongs legally to other countries. Has that been navigated? Is it like international borders?
The legalities have been, and I gave up sitting on the committees 15 years ago after 20 years. So the committees are still debating that in Vienna. So there is a Vienna Accord, and there are lots of working groups around this. The bottom line is that the real issues are not so much to do with the legalities, because debris is debris, and all countries waive their own, because they don't want to be responsible for it. If it crashes into something, they don't want to be held responsible for that either. So the traceability of debris to specific object, we know that this piece of debris came from that particular Russian satellite or this piece came from that French satellite. It doesn't matter. The standard of proof is so high that you can never prove it. So in reverse, they can't prove that it's theirs. And they don't want to, because as I say, it's nothing but a liability flying around in space. There are interesting legal issues that took 15 years to solve about how we manage the safety issues with spacecraft and make sure that we don't put a humongous laser on a spacecraft that's just going around doing its normal business. But that's all been taken care of.
When you become a fully fledged space pirate and are able to bring down satellites or debris into the atmosphere, will you be able to do it into a specific location and time? And how much will it cost to be able to have your own personal shooting star to wish upon?
If there was a genuine international approach to this, and I think that would probably be mandated, you would have at least 3 sites around the world that were working this technology. And I'm talking about higher powers than we're experimenting with. And those, with 3 sites, you could direct it into a few hundred kilometres of ocean, yes. That would be possible. How much does it cost? It doesn't make sense to start this if we can't get a deorbit cost of less than a few $1,000s per object. So our target, because just imagine what it costs to send a spacecraft up to catch something and bring it down. Now, one spacecraft can do 20 or 30 or even 40 objects, but it's still very expensive. So, I mean, the nice thing about this technology is once you build the infrastructure, it's free. EOS has built many such facilities around the world. They're all unmanned. So there's no labour costs. They all run without people and they do their job every day. So,
one thing I didn't hear you mention is any reference to computational resources. And I was wondering, are there computational issues with this program? Are you keeping track? You've got a huge amount of data to keep track of. Are you actually keeping track of all the orbits? And what percentage of your budget goes into actual computation? Is it a problem?
It was 20 years ago. I can remember we built our own supercomputers. We actually sat out the back buildings wiring together PCs in parallel until we had enough that we could reach the computational barriers. Today it's not a problem, both in storage and in computation.
From my recollection, Australia's first effort at shoving lasers out into the space was the Lunar Laser Ranger down at Royal Valley, where massive beam of light up and they expect to get about 1 photon back. I was just wondering if you've got any comments about whether that facility there assisted you in terms of where you finished up after all those years.
The background of this question is I was the Chief Technology Officer that built the Aurora Lunar Laser Ranger back in 1970. I don't want to admit which year it was. It was 73. So that technology was a great leap ahead for Australia. It was a science program, and people today take for granted so many things like continental drift. They take for granted the resolution of the conflict between Dirac and Einstein. They take for granted 100 different things. Polar motion. And I remember we built the Lunar Laser Ranger at the time, and we wanted to solve 120 differential equations for 119 variables, including continental drift, polar motion, Earth rotation, and the derivatives of those. And the experiment was ultimately a great success, and the base of it was a big telescope, a big laser, and computational smarts. And yes, this technology today started 1973 in Aurora Valley.
Okay, that's the last question we can have, I'm afraid. We have a lot more, but can we please thank Ben for that?
Thank you.
So thanks also to our audience for joining us here at the Shine Dome and online. Tonight's talk will be made available on the Academy's YouTube channel shortly. Be sure to have a look at the Academy's huge selection of fascinating talks on a range of different topics. We hope you enjoyed this talk. one of a number of public events and activities of the Australian Academy of Sciences aiming to improving public awareness and understanding of science. Other activities of the Academy include school science and maths education programs and our wonderful Science Explainer website, nova.org.au. The Academy is also a not-for-profit organisation, and I want to thank each of you who have supported us by purchasing your ticket to tonight's event. Your contributions help us to continue to bring fascinating speakers and important topics to a broader audience. If you'd like to explore other ways to support the work of the Academy or make a donation to our annual giving campaign, I encourage you to visit the Support Us pages on our website, science.org.au. The next event will be in August for the 4th instalment in the series, Australian Satellites and Where to Find Them. To find out more details on any Academy events, please visit the Academy's events page, www.science.org.au/events. Thank you once again, and we hope to see you at the next talk. Thank you.